It's a great day for Gauss-Bonnet. Today, we are going to share a proof that the Gauss-Bonnet theorem of the sphere implies the fundamental theorem of algebra. It's New Year's Eve. I hope you're having a good day. There's Murph. He's excited. Gauss-Bonnet, fundamental theorem of algebra. Let's dig in.
It's a great day for Gauss-Bonnet. This is video number 10. I'm Brad McCoy. It's December 2023. Actually, it's New Year's Eve. So, Happy New Year. So last time we talked about cubical complexes, and we had this little paradox where should this be a closed curve or not, and we resolved that. And then we looked at a paper of Chen and Rong, and they used the Gauss-Bonnet theorem to compute the genus of a cubical complex. And this was done by, measuring local curvature. So this was interesting because we're going the opposite way we normally are to compute, to use the Gauss-Bonnet theorem. We're computing the local curvatures, adding those up, and that's telling us the genus. So that was a nice example of using the Gauss-Bonnet to compute the genus, which is something we hadn't seen before. So in this video, we're going to talk about a paper of Almira and Romero, and it's the Gauss-Bonnet theorem implies the fundamental theorem of algebra. So I'll take a second here and show the picture of the paper, as I like to do. And we'll review some complex analysis. I don't spend a lot of time with complex analysis, so in order to understand this most of my time, I needed to refresh some complex analysis. So that's where we'll spend some time, and then we'll accept a few other things as fact as we get into this proof. Okay, so what does the fundamental theorem of algebra say? Also, sometimes named after Gauss, so we call it the Gauss-Bonnet theorem, so I included that. It says if we have a polynomial from the complex plane to the complex plane with complex coefficients, so here's our polynomial, it's non-constant and single variable, then P has at least one root. So just as an example here, if we say P of z is z squared plus 1, well, we know if we're in the real numbers, we can't factor that, but in the complex numbers, we can factor it, z minus I, z plus I, and so we see if this is, I and minus I, and the complex plane, these things are going to be 0. So this has 2 zeros in this case, but the fundamental theorem of algebra guarantees us at least one. And this is useful in many proofs analysis, so you can factor out a term, and some sort of induction happens often. Okay, so interesting thought on the fundamental theorem of algebra is that, most, if not all, proofs involve some use of continuity. So it's not a theorem about algebra, and it's not fundamental to algebra. So it's sort of interesting. Why do we call it that? I don't know. But it is a fundamental result, just maybe not to algebra. Okay, so let's review some properties of complex analysis, or some ideas from complex analysis, just some basic things that were helpful to me to refresh myself on. So we can write a complex number as real plus I real, or we could write things in polar form, where this is, our modulus here. And note that this is always going to be a real number, so that's useful to us. We saw the previous example, you can think of this as the xy plane, so here our i's are happening up here. Or if we have some point out here, you can think of this as the radius and some angle as well. And if we consider complex functions, we could look at the real part and the imaginary part. And for us, these are always going to be continuous functions. So that's nice. We can take derivatives of complex functions using, difference quotients, and we can verify that we have lots of nice properties. For us, we're going to be interested in the power rule since we have polynomials. Analytic, what does that mean? It's differentiable in a neighborhood around a point. So it's we're analytic at a point if the derivative exists at that point and in some open neighborhood around the point. And we'll say, so polynomials are analytic, and they're entire. They're analytic everywhere. So the functions we're going to see are going to, I think, everywhere be analytic. Is that true? I believe so. Maybe some 1 or 2 points cause us problems, but for most of the things we see, we can take derivatives everywhere. And if our functions are differentiable, you may have seen these Cauchy-Riemann equations. So we have these mixed partials are equal with the exception of a sign change here. And if we want to compute a derivative by using the Cauchy-Riemann, you can just, differentiate with one variable or the other, since we have these nice Cauchy-Riemann equations. So that's useful for computing derivatives. And then the final definition we need from complex analysis is this definition of harmonic. So if the second order derivatives sum to 0, this is called Laplace's equations, and we call such functions harmonic. And the fact that we're going to use here is the real part of analytic functions. Maybe this should say are harmonic. Or is harmonic. That's fine. Let's just leave it as it is. That's fine. So the real part of an analytic function is harmonic. So we'll see later this will come in. This is sort of a big fact we'll need. All right, we're also interested in the complex logarithm function, but in order to talk about that, we want to talk about the complex exponential. And so here it is. You could ask, well, why is this the complex exponential? Well, think about what properties we would want to have. The big one is it's its own derivative, so you could use our formula we talked about above to compute this derivative, and see that it is its own derivative, so that's nice. And it satisfies some other nice properties that we want from exponentials. Also, if we put just a real number in here, notice our y would be 0, and we would get just the real exponential back, which is desirable. Another thing to notice is this function is periodic in the I direction, since we have these trig functions there. And if we map this, look at where this sort of fundamental domain gets mapped to, we'll see it goes to this annulus, which is kind of nice. So. Okay, so that's the exponential, but we're really after the logarithm. So we think about, well, what would the inverse of this function look like? And if you spend some time thinking, you can see where this is the argument, and this is the natural logarithm of the modulus. And the second fact we're going to need is if we take the log of the absolute value of a complex function, that's equal to the real part of the log of the function. So hopefully you can see that happening here. So this is going to be a real number, and that's exactly coming from the definition of the complex logarithm. So complex logarithm, so this is fact 2. All right, so that ends our little tour of complex analysis. The other thing we want to remind ourselves is stereographic projection. We saw this in an earlier video, I believe. But if you have the sphere and you remove a point, you can get a map from the complex plane or the R2 that has some nice properties. So here you can say, well, we mapped this point on the sphere to this point on the plane. And this map stereographic projection is what's called conformal. That'll be important to us, meaning it preserves angles, circles, and orientation. So what that means is if we have some circle on the sphere here, that would get mapped to a circle in the plane and vice versa. So that's certainly a nice property. Yeah, maybe I should have spent more time on stereographic projection, but that's okay. It exists and it's conformal. I think that's all we'll need for this video. All right, so back to our proof. Here we go. So we're trying to use the Gauss-Bonnet theorem to prove the fundamental theorem of algebra. So what we want to say here is we're going to go for a contradiction. So here's, say you give me some polynomial, and we're going to say we're going to require that a naught and an are not equal to 0. So hopefully you can justify why we can make that assumption if they were 0. And we're going to go for contradiction. So we're going to suppose this is non-zero for all z and c. And this is just so creative, sort of really like this proof. What do? We build a p star, and we notice p star by switching the coefficients. So we had, instead of, we'll have an with no z term, and a0 will get paired with z to the n. This has nice property related to p for non-zero values of z. And we can build this function f by multiplying p and p sub star together. And this function f has some really nice properties too. I don't want to get bogged down. This is just such a clever creation. I don't want to get too much into this properties, but it has some really nice properties. And it's going to allow us to define a metric on the sphere. So the C hat, did I define this? This was the complex plane union infinity. And we can say, well, if if Z is an element of C, so not infinity, that would be our blue here. We can define a metric, no problem. And if we do include infinity but not 0, this would be the red here. So we include infinity, but we're going to kick out 0 and use everything else. And the idea here is we take something on the sphere, use our stereographic projection, map it to the plane, use this F to come up with a volume element. And that's going to be our metric on the sphere. And then we use these nice properties of F to take care of, well, what if we're infinity? Okay, we're okay. And what if we're at 0? We're okay as well. So for any small region on the sphere, we get this area element. So very clever construction. So cool. Okay, so let's combine some of our facts we've seen, and we'll hit this proof here. So we can use, if our map is conformal, which it is, stereographic projection, we can compute the curvature in terms of these G values. And here we see our Laplacian and our logarithm. That's why we spent some time on this. The paper says this is like a standard thing, but it wasn't standard to me. So there is a proof of this in GTM. So this is called Modern Geometry by Dubrokin, Fomenko, and Novenkov. Hopefully I said those names right. Sometimes struggle with names. But yeah, so we can compute curvature in terms of this new metric that is given by our non-zero function, P, that we built up there. Okay, so that's one fact. Again, a part of me wanted to spend a long time on this, but I'm not going to. So if you don't believe me, or this seems unintuitive to you, maybe see this textbook where there is a proof of it. So, okay. And just collecting our other facts, we have the real part of an analytic function is harmonic, and this nice fact about complex logarithms we saw. Okay, so back to our proof. So we're on the sphere. And so we can take the curvature at any point. So pick a point, any point. And then we have, okay, so what is our curvature? We have our curvature. This is some positive number. We can rewrite this using our metric. So this is fact number 3 here. And then we can use, what are we doing here? So this is our fact, what did I number this? This is fact number 2. So using, just rewriting our logarithm here, using fact number 2, and then using the fact that the real part of an analytic function is harmonic. So this is by fact 1. This gives us a 0. But why is this a contradiction? Well, we know by the Gauss-Bonnet formula that the integral of our curvature is equal to 4 pi, 2 pi times our Euler characteristic. So there must exist some point where the curvature is positive, if we're going to get a positive answer out of this. But our non-zero polynomial told us that the curvature at every point is 0. So this is a contradiction by Gauss-Bonnet. So this is very cool, you know, just so neato. Okay, so just to recap, yeah, we have this way of rewriting curvature. Well, first we cooked up this function f based on our polynomial not having a 0, and this function f had these great properties. We used stereographic projection to come up with this nice metric. We then used some facts from complex analysis, fact about the logarithm, and fact about analytic functions. So that was pretty neat. So that's our recap. So Gauss-Bonnet theorem implies the fundamental theorem of algebra. Oh yeah, that's it. I'm probably going to take a little break from making these videos. Thanks for tuning in. So I'm not going to say I'm done forever, but that's the end of season 1.